We now have our epipolar constraint, which essentially tells us that there is a single 3 by 3 matrix, the fundamental matrix that we need to find to calibrate our uncalibrated stereo system. So our goal here is to estimate the fundamental matrix. To do this, here's what we're going to do. We're going to first find a small number of corresponding features in the two images given to us. Of course, these images have been taken from different viewpoints, so features are going to look somewhat different. But if you apply something like SIFT to the left image and the right image, you're going to get some good matches between these two images, despite the fact that the viewpoints are different. So let's say that these are your matches right here. You get image coordinates in the left image coordinates in the right image. And let's take one of these corresponding features. Pairs of image coordinates in the left and right images. And we're going to plug those into our epipolar constraint, which is right here. And in our epipolar constraint, we know that now the image coordinates ULI and URI are known. And what we're looking for is this 3 by 3 matrix, which is the fundamental matrix. If you simply write out this expression, you get this linear equation right here. And you get one such linear equation for each scene point, which produces corresponding points in the two images. And so you simply stack up all of these equations, and you can then rewrite them in this form where you have a single matrix here. This matrix we'll call A, where everything in A is known because it only includes the image coordinates in the left and right cameras. And then you have a vector F here, which is essentially your fundamental matrix written as a vector, all of its 9 elements. And then you have 0 on the right-hand side. So you have AF equal to 0. Familiar form, we've seen this before. A is known. Now, that brings us to the issue of scale. So if you essentially look at the fundamental matrix, it is acting on the homogeneous coordinates, image coordinates of a scene point. And so you have this expression right here, which we've seen before, let's say for a particular scene point. If you simply multiply this with k, or multiply the fundamental matrix with k, it doesn't really have any impact on the image coordinates. The two are still equal to 0. In other words, the fundamental matrix F and the fundamental matrix K times F describe the same epipolar geometry. That is, F is only defined up to a scale factor. Another way to look at this, which we've discussed before, is that if you take a stereo pair and a world and you take an image, two images, and now you simply scale up the entire system, that is, you double the size of the world and you double the size of your stereo system, you're going to end up getting the same images. So F is only defined up to a scale factor, and so we can then set the scale of X, so to speak. And one way to set the scale of F is by saying that F squared is equal to 1. We use this particular way of doing it because it's convenient in the way we wish to formulate the problem. Once you've done that, we can solve for F. Turns out to be a least squares solution, where we say that we want to find the F that minimizes AF squared. This is from our epipolar constraint and the equation that we got, and such that F squared is equal to 1, which is essentially saying we are fixing the scale of F. And this is a form that we have seen many times in the past. We saw this in the case of estimating the projection matrix during camera calibration. So we know this, we know how to solve this. It is the constrained linear least squares problem, and it ends up being equivalent to solving an eigenvalue problem. And at the end of it, you get a solution for F. And then we rearrange the elements of F to get the fundamental matrix F. So rearrange the vector F to get the fundamental matrix F. So now we have the fundamental matrix, and we know how to compute the essential matrix from the fundamental matrix because we know that E is equal to KL transpose FKR. And we know KL and KR. Once we have the essential matrix, we know how to decompose it using singular value decomposition into the translation matrix and the rotation matrix right here. Once we've done that, our uncalibrated stereo system is now fully calibrated. So where are we in our process? We have calibrated our stereo system. The next thing we want to do is to find dense correspondence. Ideally, for every point in the left image, we want to find the corresponding point in the right image. Once we've done that, we want to triangulate and compute depth.